All right, welcome back. So let's continue talking about inductance today. Quickly, last time we talked about if you have a coil or solenoid in the circuit, then as the current increases with time, then the coil actually doesn't like it because now the changing in current induces changing in magnetic field. So the coil doesn't like the change of magnetic field. So you'll have an induced back EMF opposed to that change. Okay, so then there's a back EMF for the coil when the current is changing, either increasing or decreasing. So that property, the resistance of the coil to the changing of current is called inductance. Definition of inductance, so it's related to the change of time, current over time t, and that gives you the back EMF. Or you can again use the Friday's laws. Just look at the change in flux over time t, and then times the number of turns of coils you have for the magnitude of the induced back EMF in this case. The inductance is in the SI unit of Henry or H, that is equivalent to volts times second over amps. Okay, so then back EMF is equal to minus L di over dt in the differential form. Okay, so if it's changing with time, then in general is the equation you can use. Now, special case, if the changing rate is constant, you can use this delta I over delta t. So L can also be equal to, you can use these two relationship, these two equal to each other. So N delta I, delta phi over delta I, because delta T and delta T cancels. L then equals to, if you just start from this expression, then it's the epsilon over di over dt. L should be just a positive number, okay? For the solenoid in the circuit, so then the inductance, you can also relate it into the its specifications, the number of turns per unit length, and then the area and with the length. Okay, so you can derive it. So starting with B equal to mu naught Ni, and N small n will be equal to capital N over L. The flux change, so you are thinking about the scenario of the current goes from 0 to the final number I. So the flux change, then you can calculate, okay, or the final flux that will be equal to the flux change divided by the current change, okay. So then gives you as the final result U0, U mu sub naught N square AL, and solenoid used in the circuit is called an inductor because it will have inductance. We talk about mutual inductance. That means if you have two coils close to each other, if there's one change in current in one coil and then in the second coil, then there will be induced back EMF. Okay, so the change in current in the first coil produces changing magnetic field in the location of the second coil. Hence, there's a back EMF on the second one opposing the change of the magnetic flux through it. So this interaction, it's called mutual inductance. We use symbol M. Okay, so for the self-inductance, we use L, but for mutual inductance, we use M. So again, you can use the flux change divided by the time, the current change, and then multiply by N turns of the coils for each of them. So you can calculate them differently using flux over current, either way, okay? Or you can use the from the definition from epsilon produced equal to minus m di2 over dt, okay? Or if you are looking at epsilon 2, then it's minus m di1 over dt, so either way. So we also look at the energy in the magnetic field. So this is in terms of inductance, because if there's current in the inductance, it produces magnetic field in the inductance. Okay, so then specifically in that sense, we look at the dimensional analysis of the equation that we get from the Kirchhoff's loops rule. So then it turns out Li di over dt is the power for its dimension. So it represents the power delivered in the inductor. So then we can calculate what will be the work by doing integration of the power times dt to get us. It turns out the energy in the inductor is 1/2 Li squared. Okay, L will be the current, I will be the inductance. And specifically for solenoid, we can further analyze it. So then it turns out the energy is equal to 1/2 Li square, and then for the solenoid, L is specifically equal to that guy, and then I will be B over mu naught M. So it turns out to be B squared times AL over 2 mu naught. So it's a magnetic field squared, and then this gives the volume of the inductance, the inductor, and then divide by the constant number. Okay, so it's proportional to magnetic field squared. And if you look at the energy density, magnetic in energy density, you divide by the volume, which is A times L. So then it's purely just B squared divided by a constant number, or a constant number times B squared either way, because inverse of constant is still a constant. And then early in chapter 8, we learned that for the electric energy density is also just proportional to the electric field square. So these two then is similar to each other. So energy density in the magnetic field is proportional to B square, and then divided by 2 mu naught. Energy in the electric field is equal to E square, and then multiplied by a constant number, 1/2 epsilon naught. Okay. All right. So today we will be looking at the RL circuits. So we will take a detailed look on the RL circuit. Okay, so when you have RL circuit, when you have the switch on, then the current goes from 0 and then build up in the circuit, right? So Kirchhoff's loop rule will tell us that epsilon naught minus L di over dt minus IR equal to 0. Okay, so that's this guy. You start from here and then through this guy and coming back. Okay. So you can solve for this differential equation, and then it turns out the current will be equal to epsilon over R, 1 minus e to the minus R times T over L. And then because R and L are constant, we can group them together. We call it a time constant. Tau. So tau as a time constant in this case is L over R. For the RC circuit, if you remember, tau is equal to R times C. So in this time it's L over R. Okay, so slightly different, but this is the time constant here. All right, so this is the result, but let's take a look on how we get to that result. Okay, so let me show you the how to get to that result. All right, so we have this Kirchhoff's loop rule gives us this equation, epsilon minus L di over dt minus IR equal to 0, right? We'll be solving for I in terms of t. So we are going to put di in one side of the equation and then dt in the other side of the equation. So to do that, first, epsilon minus IR equal to L di over dt, okay? So everything that is associated with I will be go on the same side as di, and then the rest you can put them on the other side of the equation. So that's do dt on the left-hand side and then L to the right-hand side. But this term has I in it, so you'll do dt to this side, okay? So over L, kind of like a cross multiplication, right? So epsilon minus IR over 1, right? So then cross multiply. All right, so that equals to, and then di will be over epsilon minus IR, okay? Then you integrate. So starting from 0 to the final t, and then on this side from 0 to the final current. On this side, it's just dt with constant number, so then the result should be L over t, and then 0 and t. On this side, this is di over epsilon minus IR, okay? So the variable here, I, is also here. So this result is actually natural logarithm function, but with the R there, so then it becomes and minus there. So minus 1 over R, natural logarithm of epsilon minus IR. Okay, so that's the result for the integration. The limits is from 0 to the final current. Okay? On this side, it's just T over L. On this side, you plug in this guy and then minus plug in that guy. Okay. We can also just make this guy goes to the other side of the equation. Okay, so then on this one, it'll become minus R T over L. Okay, so then natural logarithm of epsilon minus IR minus natural logarithm epsilon minus 0. Okay, so then that's it. Okay, so on the right hand side becomes this. Okay, left hand side you have minus RT over L. Now you need to solve for I, right? So exponential on both sides. So e to the minus r c over L equals to epsilon minus IR over epsilon. So this becomes 1 minus I times R over epsilon, right? So then exponential minus RT over L. Now still need to solve for that guy. So you can move this to this side. Equation becomes positive I times R over epsilon equal to 1 minus e to the minus RT over L. Okay. So then multiply both sides by epsilon over r, the inverse of this guy. Okay, so I equals to epsilon over r, 1 minus e to the minus r t l. Okay, and this is what you have on the PowerPoint slide. And then also by writing the time constant tau as L over R, then you get this. Okay, so that's the result there. Okay, so this derivation of the what you get in the PowerPoint slide. So let's go back to a PowerPoint slide. All right, so now we have this guy derived. So then this is a time, this is a current, okay, as a time function in the whole circuit, and then this will be the time constant L over R, okay. On the inductor, the voltage on the inductor is this term minus L di over dt, so it's the second term. So you can, because now you have I there, you can do derivative of that guy. So pretty easily, derivative are basically two terms, right? So these two each multiplied by that guy, but derivative of the first one will be constant, will be 0. So then it will be just derivative of the second one. Or we can look at this guy, maybe easier, because the first term goes to 0. The second one will be epsilon over r. Now e to the minus rt over L still remains times r over L, because according to chain rule, anything in front of t should come out. Okay, so minus L over t. So then you'll get L and L cancel, you'll get epsilon over L, and but there's a L in front, so then that goes away. So minus epsilon e to the minus t over tau. Okay, so this is the voltage on the inductor. So if this is equal to 0, right? So then this whole thing is equal to 1, so then it's minus epsilon. So we start with the back EMF as maximum as the batteries, and then decreases out. Okay, so decreases out. So this is kind of similar to the discharging process for a capacitor. So now the other way around. Okay, start with a maximum back EMF and then dies out. The current start with 0, right? Because when t equal to 0, this thing is 1, 1 minus 1 is 0. So start with 0 and then goes up. Okay. So again, this is in the opposite to the RC circuit. For when you are charging the RC circuit, the current the voltage goes up. In this case, the voltage goes down on the inductor, and then the current actually goes down for the charging process. But in this case, it goes up. Okay. All right. So current goes up, voltage goes down. Let's take a look on this example here. So let me show the work on the paper. So this one says, how much time does it take for the current in the RL circuit with R equal to 130 ohms and L equal to 68 millihenry to reach half its final value? Okay, so the current, right, as a time function, this is what you have. So this guy or that guy. So we'll take probably this one, okay, and then we'll type in that guy. So I as a function of time t equals to epsilon over r, 1 minus e to the minus t over tau, okay, tau being L over r. All right, so giving R and L 68 milli 10 to the minus 3 Henry. So you can calculate tau, okay? But anyway, we are looking for when the current is half of the final. So what would be the final value of the current if you have this RL circuit closed, right? Final, that means when t equal to infinity, right? So you can do that. So you can calculate what's the I final first. I final. When this is infinity, so minus infinity over tau, right? So that's minus infinity. So e to the minus infinity is 0, right? E to the infinity is infinity, 1 over infinity, that's 0. So then that would be equal to epsilon over R. Okay, that's the final. So it says you're looking for I of t when this is equal to half of that, so 1/2 of that. And I of t is also equal to epsilon R, 1 minus e to the minus t over tau, right? So then you basically would just set these two equal to each other and then solve for t, okay? So 1/2 epsilon over tau over R, epsilon over R, 1 minus e to the minus t over tau, okay? So 1/2, the epsilon over R will cancel. 1/2 equal to 1 minus, right? So that means this is 1/2, right? So e to the minus t over tau is equal to 1/2. So then natural logarithm for both sides of the equation, natural logarithm of 1/2. So this gives you minus t over tau, but on this guy gives you minus of ln of 2. Okay, so minus minus actually kind of cancel. T then equal to ln 2 times tau. Okay, so L over R ln of 2. Okay, so we can plug in the numbers there. 68 10 to the minus 3 Henry over R, 130 ohms, and then ln of 2. Natural logarithm of 2. Okay, so that gives you T equals to 0.363 10 to the minus 3 seconds, or 0.363 milliseconds. Okay, now you want to say 3.63 times 10 to the minus 2 seconds, or minus 4 in that sense. Okay, so that will be also fine. All right, so going back to the slide. All right, so let me try to get out there this bar to be on top. Okay, so when you have circuit like this, you have two switch. If this guy is closed, then you are kind of charging this RL circuit, okay? And with this open, this closed, then it becomes this guy because this goes away, okay? So it becomes this. So it's named because we have current built up initially in this inductance, so then there's energy stored there. We can then have this one open, this one closed. So then we withdraw energy from this guy. Okay, so then it kind of flow out from this to this guy. Okay, or sorry. So initially, when this is closed, then you get this circuit. After the current stabilized, reaches final current, then you have this one open, this one closed, then you have this guy. Okay, so this is charging, kind of charging, discharging. Okay, or storing energy here, and then withdrawn energy from the inductor. Okay, so this is a kind of discharging process similar to RC circuit. So in this case, now you'll just have R I times R plus L di over dt equal to 0. Okay, so then you have two elements there. Again, solve for the differential equation, you'll get this equation. So I'll have you guys do that. So just follow what I did earlier for the charging kind of charging process. But then you'll get this. Okay, so once you have that, then voltage is L di over dt, then you'll get this, okay, on the inductors. So then current for this kind of discharging process, it goes down for right now, okay, and the voltage will also go down, okay. Okay, let's Let's take a look on another example here. It says given the circuits showing here. So it's asking you find current in the battery here, and then in the resistor, and then in this guy, okay, at all different time given list here. So let's take a look. So let's redraw the circuit. If you want, you can pause it and then maybe skip the time I'm drawing this, okay? So there's a switch, there's a battery, plus and minus. There's 10 volts on the battery. And then there's a resistor, which is 10 ohms. And it's connected to on this branch of the circuit, there's an inductor. Okay. And then on the other side, this is resistor, 100 ohms. This guy is 2.0 Henry, 0.00 Henry. Okay. So you can see as this is closed, current will go through here and then here. Okay, so it's kind of like you have two parallel circuits or two parallel branches. Okay, so current goes down there, current goes down there for 1 and 2. For A, looking for the current, okay, in the battery, and then the resistor, and then this inductor immediately after the switch is closed, okay? So the current goes out, if this is closed, current goes out, and then split into two, right? So this is I for the L, and then this is I for the R. On this side of the circuits, this is this RL circuit, right, of this guy. And then on this side, there are two resistors in parallel to in series, okay? So on this, we can think about like just two part of circuit, okay? So on one part and then the other part. So I of R through the resistor should be simply just the epsilon over the 100 plus the 10, okay? So will be 10 volts over 110 ohms. So that gives you 0.091 amps, okay, on the resistor, the 100 ohms resistor. Now for the IL, we'll use then the equation. So this is a charging process for this guy, right? So it'll be the epsilon over R, 1 minus e to the minus t over tau, where tau is equal to L over R. So immediately after that is closed, t equal to 0. When this is equal to 0, this thing is equal to 1. So 1 minus 1 is 0. So then I of L is equal to 0. Okay. So on the inductor, so the total I on the battery should be equal to I of the resistor plus I of the inductor. So 0.091 amps. Okay. Now on B, it says find the current again, the current through those three battery, 100 ohms, and then the inductor. Long after, okay, so long after again on the resistor, because on this side it's just a resistor with battery, so it should be stabilized, okay? So that R will be still 0.091 amps as we have, okay, the same for the resistor. Okay, IL, this is again epsilon over R, 1 minus e to the minus t over tau, okay? And this time, this is equal to infinity, t equal to infinity. So then this whole thing will be 0, okay, 0. So then it will be just epsilon over R. And this R is the 10, okay, not the 100. So don't mix up with those, okay, over the 10 ohms. So 1 amps, 1.00 amps, okay. I think everything should be 3 sig fix. So It should be still 0 after the 0.091. Okay. Okay, so then on the battery will be these two add up, so 1.091, okay, amps. I'm sorry, actually not the case. So after a long time here, the current will just go through. Okay, so this is then acting as a straight wire because the current stabilized, okay, and then just go right through. Okay, so t equal to infinity. This becomes a straight wire. Okay, it's no longer having the resistance, okay, to the current or the inductance. So in that case, you're looking at this side of the circuit and this guy. So if this is straight wire, the electrical current is lazy. You will just prefer go to this guy and not going through the at all. Okay, so I made a mistake. So this guy will be 0. Okay, so I on R, the R100 now will be 0 amps. Okay, so then this will be just equal to, for the battery, it will be equal to this 1 plus 0, so be 1. Okay, so sorry about that, about 1.00. Okay, because 1.00 amps, because now long after the switch is closed, this guy, the inductance is no longer affected because you have no changing in current. So then this becomes a straight wire. Okay, so straight wire, the current will choose to bypass anything else. Okay, but the straight wire. All right. So then now going back to going down to part C, find again current through the battery resistor, 100 ohm resistor, and the inductor. When now this switch is open again, so the switch now is open again. It's open, back to open. Okay, so if this is open, then this branch is cut off, right? So there should be no current in the battery. So the battery should have 0 current. And then initially there's current going through there, so there's energy stored in the inductor. Will now to go through this guy, okay? So then consumed by this one. So current goes down here and then goes up there. So these two should have the same current, right? So the current in this inductor now as the discharging for the inductor. For the discharging, you can look one slide back. For the current is epsilon over R. Now e to the minus t over tau, sorry, over tau, when t equal to 0. So t equal to 0, this thing now equal to 1 again. Okay, so this will be then epsilon over R again. It's just the 1.00 amps, okay, to start with. And then that's the same for the inductor and the 100 ohm resistor, okay? And then the battery will be 0. Now, long after part D, long after this is closed, okay? So then this t now becomes infinity. So if it's infinity, then minus infinity, right? E to the minus infinity is 0. So everything then will be 0. So I on the battery is going to be 0. I on the inductor and then I on the 100 ohms resistor should be also 0 because now you have used up the energy stored in the inductor. Okay. All right. So we'll go back to the slide. Okay. Now moving on to the next section. So we have learned by now, if you have inductor, so you kind of store energy in the form of magnetic field in the inductor. And then earlier, before we talk about magnetism, in electricity, we talk about the capacitor actually stores energy as well. Okay, so what if now you have just a resistor or not inductor and a capacitor in the circuit, right? So what happens is depends on what you start with. So initially, let's say you have charges on the capacitor. So then this will produce current, okay, in the circuit. So then you will discharge the capacitor, but then you create current in the circuit. So the current then goes to the inductor that gives you the energy in the inductor in form of magnetic field. Okay, so originally energy is in form of electric field. Now it becomes energy in the inductor magnetic field. So then after that reaches maximum, your then energy will now going back to the capacitor. So then the positive charge going to that plate and then negative on the top. Okay, so this case. Okay. So then will be fully charged, then current goes to 0, okay, and then they will go back again. So this kind of going back and forth, okay. So there's charging and discharging process for the whole circuit. So then on the capacitor, you'll see charge goes up and down. On the inductor, you'll see the current oscillate as well, okay. So the total energy stored then on the circuit should be 0. Okay, so then we're just coming back and forth, back and forth. If there's no resistance in the circuit, then this will go forever. But in reality, right? So we know we should have wires connecting there. So wires will have very small resistance, and will actually absorb all the energy at the end. Okay, it's just like a pendulum or the mass attached to a spring, right? Because of the air resistance, it will die out eventually. Okay, but energy, if there's no resistance, right, then this is oscillation will go forever. Okay, so LC circuit is similar to a mass attached to a spring. So where you have transfer energy between the mechanical energy and the elastic potential energy, so mechanical energy and potential energy back and forth, back and forth. In this case, the LC circuit, you have the energy in the magnetic form and in the electric field form back and forth, okay? So for the mass attached to the spring, you can do the displacement as a function of time t cosine function, right? It's oscillating back and forth. Similarly here, we'll be for LC circuit, we'll be looking at the charge as a function of time t. So that should be also a cosine function, okay? And then if you do dt over di, that gives you the current in the LC circuit as the sine function, okay? So the frequency of the oscillation of the LC circuit, okay, so it will turn out to be angular frequency equal to square root of 1 over LC. And then angular frequency is equal to 2 pi times the frequency. So if you want to calculate the frequency, you can calculate that way, okay? All right. So let's take a look on LC circuit. So the application of LC circuit is in the radio tuner. Okay, so you have like L and C, and then of course there will be a resistor in place as well. But let's take a look on here for LC circuit in the AM tuner in the car stereo. Uses a coil with an inductance of 2.5 millihenry and a variable capacitor. So the capacity can go from a certain range, so then you can tune to different stations. They have different frequencies, okay? If the natural frequency of the circuit is to be adjustable over the range of 540 to 1,600 kilohertz, okay, which is the AM broadcast band, what the frequent range the capacitance is required, okay? So looking for the frequent range for this capacitor. So if you tune to the resonance frequency of the tuner, and if that resonance frequency match up with a certain radio station, then you will receive signal from there because that signal will be amplified. Okay, so then we'll be looking at the natural frequency of the tuner. Okay, which is equal to omega is equal to 1 over LC and then square root. So frequency is 2 pi or 2 pi frequency is equal to omega, okay? So it gives us that 500 or 540 kilohertz is in the range of frequency, right? Kilohertz. So then we are actually doing for this tells you frequency is actually omega over 2 pi, and then omega is that guy. Okay. So then this is 2 pi and then 1 over square root of LLC. Okay. So substitute this in this here. 540 kilohertz or 10 to the third hertz is less than 1 over 2 pi L. C. L is given, so 2.5 10 to the minus 3 times C less than times 10 to the third Hz hertz. Okay, so then solve for the C, the range for the C. All right, so first you want to square everything. Square, and then square. Okay, to get rid of the square root on the C. Okay, so and then you'll get 4 pi to the square, right? So this everything will be now multiply everything by the constants. Okay. All right. So in the middle, you'll just simply have 1 over C because square root on CB squared. Okay. Less than, now you move this 2 pi and then square root of 2.5 times 10 to the minus 3 Henry. Okay. Multiply by the 540 times 10 to the third hertz, and then to be squared less than, again, 2 pi square root of 2.5 times 10 to the minus 3 Henry times 1600 10 to the third hertz, and all to be squared. Okay. So this whole thing gives you 2.88 times 10 to the third less than 1 over C and less than 2.53 times 10 to the 11. And then you do inverse, okay? So inverse of that gives you on this end, this is going to be 34.7 10 to the minus 12 F. I play around with the scientific notation. So then this is in picofarad, okay? 10 to the minus 12 is pico. Greater because you do inverse. So then the sign, the flip, okay? C and then greater than 3.96 10 to the minus 12 farad. Okay, so your C has a range of 3.96 picofarad to 34.7 picofarad. Okay, so that's what you would have. All right, going back to the slide again. Now, in reality, there's always certain resistance on the circuit, so then you always get that R on any LC circuit. Okay, so then the whole thing will die out eventually. So that's the damping oscillation. So for damping oscillation, you can write it out. Okay, so this is what you have. Get the power on the capacitor, and then this is the power on the inductor. This is the power on the resistor. Okay, so then this is differential equation. You can actually solve them. The result should be a cosine function, or cosine function would be one of the solutions, and it gives you this guy. Okay, so it dies out, right? And then you'll have when this guy, this is similar to like just the damping oscillation. Okay, so then the result there. Okay, so the solution there, and then omega prime is this guy. Okay. All right, and you can also goes back to the when we have the harmonic oscillation to see this. Okay, similar result there. I think we'll just stop there, and then we'll come back next time. Okay. See you guys.